Can you hear me now? Okay, good. All right. So one thing I forgot to mention last class is whatever I'm writing, it is linked to on the class website. And for instance, if you go to here, you see course notes. If you click on it, you can see the sheet that I'm writing on. You can also see it updated in real time. So it's always available for you to peruse and use. And each lecture is going to be on a different sheet. Okay. So just make sure you're looking at the right lecture notes. Okay. First, let's look at some examples, as I said. Okay, hold on. I see my screen over there. We're not here. Okay, there. Wow. Color is quite bad. Okay, so if you go to the workspaces tab, you will see various things to play with. And one of those is this. Hope you can read it. Okay, so let's just plot some empirical risk minimization objective functions and see what they look like. Okay, so the first stuff is just some boilerplate code to just plotting functions. Okay, so let's generate some data of the form, you're generating a bunch of examples and labels. And the labels I'm using are just random linear function labels. Okay, so you have two-dimensional data, 10 examples, generate some noisy data where the labels are w star.x plus some noise. Okay, and you can set up standard empirical risk minimization problems as we need. And you can have L2 loss, you can have L1 loss. You can define a family of prediction functions. Remember, to set up ERM, we need to decide the loss function and the class of predictors you're going to use. Okay. And let's see what kind of surfaces we get if we use, let's say, L2 loss or if we use L1 loss. Why is this so slow? Yeah, for some reason, when I connect to the HDMI, it's hanging. Okay, let me try one last time to figure this out. Okay, so if we use square loss, the surface looks like this. I don't know if you can see, the projector is pretty awful, but it's a much smoother surface. And this is the contour plot. So you're looking at all the points with the same objective function value. And there's something nice here, like, you're seeing this nice ellipse structures, right? That's again going to play a role later on. And this is for squared loss, right? So we did least squares regression last time. The loss function is just a minus b whole squared. If we use that as a loss function, this is what the objective function looks like, right? We're in 2 dimensions. There are 2 parameters. So for each possible theta, which has 2 values, there's a corresponding loss function. And this is what the plot of that loss function looks like a nice bowl. Okay, it's kind of, not very symmetric. but it is still a bowl. And if I project it down to two dimensions and draw the contour plot, this is what it looks like. So the blue values are the smaller ones, the red values are the bigger ones. And if you want to minimize, we want to get to a blue value from wherever we are. Okay, bluer the better. And we can also see what happens if you have L1 loss. Okay? If you have L1 loss, it is still kind of like a bowl, but it's not a smooth bowl. There are creases. Okay? They're kind of flat surfaces. L1 loss just means that your loss function is absolute value of A minus B. And if you draw the contour plots, you can once again see it is still somewhat nice, but you don't have the ellipse structures here. You have like this polygonal cross sections. Okay. And kind of this goes back to what we said, the absolute value function is not differentiable. So there are some discontinuities, but you could still use gradient descent. And we also saw the discrete loss, right? Let's say you have binary data. Then one of the loss functions we said was, just check whether your prediction matches the label or not. So it was 0 or 1. Okay? And in this case, you can see the loss surface is very, very weird. Okay? So among all these three things, if you see the plots, you would guess which one would be the easiest to optimize. The L2, right? The bowl. L1 maybe is second best, and the 0-1 loss looks nasty, right? And the contour plot of the 0-1 looks something like this. Okay. And there's one very interesting thing here is if you look at the discrete loss, then there are a lot of values which actually give you 0 prediction error. Okay. So there's not a unique minimizer for your loss function, which can happen. Your loss function, whatever you have, might not have a unique minimizer. There can be many minimizers. Sorry?
Any intuition between the lines?
It's just color grading. The way it's drawn, it's only there's some threshold around which it starts plotting them, right? So that's where if it's a discrete loss, the values are changing discretely, right? So this is the contour plot, meaning all values of a certain color have the same function value. Okay, red is higher, blue is lower, and like these values are kind of going down. And the x and y axis are your parameter values. The theta has two values, right? Theta 1 and theta 2. So for instance, it's saying if theta 1 and theta 2 are like 1.5 and 1.5, then your loss function value is 0. Okay, and if it's like minus 1.5, 1.5, the loss function value is almost 1. Okay. And okay, it's hung again. Okay, it's coming. And we also plotted hinge loss, okay, which is again somewhat of a discrete function. It's nicer than 0-1 loss, but still not as nice. And this is what it looks like. Maybe I should download them next time. Okay, so in any case, by changing just the loss function, right? The prediction family is staying the same. You're only changing how you evaluate two label predictions, right? Squared loss, L1 loss, 0-1 loss, hinge loss. Okay. Okay. All right. Now, while this loads up, let me try it one more time. Okay, so now let's see what happens if you run gradient descent on some of these functions. Okay, so here's the gradient descent algorithm that we talked about. You start with some initial step, initial starting point, and you take a sequence of steps where in each step you update your current iterate by negative of the gradient, right? And the step size determines how much you move along it. And usually you only keep track of your current set of parameters, but here just for kind of illustration purposes, I'm tracking the entire trajectory. What is the sequence of points that gradient descent is going through? And in this function, the only thing it needs is another, like a handle for another function, which gives you the gradient. Okay. So that's kind of the nice thing about gradient descent, right? We said the only thing that it needs to run is some kind of oracle or function call, which tells you what the gradient is. It doesn't need to know anything else about the function you're trying to optimize. Okay, and let's see what happens if I run it on a very simple function. So the function I'm trying to minimize has two parameters, a comma b, and it's just a squared plus b squared. Okay. Where is the minimum? The minimum is 0, 0. The function is always non-negative, and the least possible value is 0, which occurs only at 0, 0. So you can define, the function, the gradient is just 2 times a comma b, and let's just run gradient descent on it. And this is what you get. Okay. So this is gradient descent with various step sizes, right? Depending on the step sizes, you're kind of having different convergence rates. Does the plot make sense? If I have step size something like 3, I start from here and I do something like this, right? If I take step size 5, somehow I'm going like this. And each time you're starting from a random initialization point, so that can change where you're starting. Okay. And in all of these cases, you're quickly converging to the actual minimum, which is 0, 0. Right? So the loss function value is actually going to 0, which is what we want. Now, what happens if we try it on, let's say, something a bit more complicated? And you can see it here more clearly. This is on the contour plot. You start from various points and then you kind of quickly move towards the center. Okay. So they're actually converging to the true optimum, which is 0, 0. And here you can see the things kind of slowly moving towards the 0. And the step sizes, you can see when they change the step size eta, some things kind of start moving faster, some things start moving slower. Okay, but all of them are doing what we expect them to do. And what happens if I'm super aggressive with the step size? Okay, so here step size is 0.1, 0.2, 0.3, 0.5, and in one of them the step size is 1. And almost all are converging to the true minimum, which is 0, 0. But when the step size is 1, you're not going anywhere. Why do you think that is? Yeah. Exactly, right? That's the thing that we said, when you're doing, if your function is like this and you take a big step, you might have just jumped across the minimum and landed on the other side of the ridge, right? So you did not make any progress. And you can see it happening directly here when you choose a big step size, right? So you need to be a little bit careful in how you choose the step size, even for a simple function like a square plus b square. Okay. Yeah.
So in this scenario, that step size 0.5 is better than 0.1.
Right. I mean, yeah, exactly. Right. You want to choose the biggest step size that works. And at some point, it's going to overshoot. And I mean, okay, in some sense, like the difference here for this problem is not that big because it's so nice. But sometimes, you can clearly see the black is like basically there, right? In a single step, it went all the way. Green is a little slower. Okay. And the oscillation you can really see in this plot, right? So when step size is 1, you're jumping from here to here, back and forth. Nothing is happening. What happens if you do L1? You kind of see the same plot. The one thing that you have to keep in mind is for L1, which is the absolute value of loss, you have to, it's not differentiable, but we said you can use subgradient. Okay. And one subgradient for the absolute value function is just look at each point. If it's positive, set your subgradient to be 1. If it's negative, choose your subgradient to be -1. Okay, because absolute value looks like this. On the positive side, the slope is 1. On the negative side, the slope is -1. Okay. But in any case, as I said, computing derivatives and subgradients is, we have tools for that. And we're working with the assumption that you have those things handy. And the same thing happens. If you choose a big step size, you might oscillate without making any progress. Whereas for reasonable step sizes, you are converging to the true minimum value. Okay. And the contour plot, as I said, to have L1 loss, it looks beautiful, but it's not spheres, it's polygonal, right? Because it's kind of like you're drawing these lines, hyperplanes, and you can reason about this geometry pretty clear. Any questions about this? You can see once again, the step size is 1, you're jumping from one side to the other without making any progress, whereas everything else is kind of going okay. Blue is converging to the least value, but is slowest because the step size is smallest. Yeah. Yeah, exactly, right? You might have multiple subgradients, and there are very, very few cases where the choice of the subgradient matters substantially. Typically, you want to use a subgradient which has, which is kind of reasonable, right? Like in the sense that if you have an absolute value function, -1 is a subgradient at 0, but so is -0, 0.1. But choosing that the latter would not be as meaningful because you want to take bigger steps. Okay. And now let's try it on a weirder function. And the function that I want to try it on is the difference of two squares. So on a square plus b square, we said, it's a nice bowl. The minimum occurs at 0, 0, so you should converge. But what if I try it on a square minus b squared, and I put minus 0.1 to kind of cause some distortion to not be symmetric? So what's the minimum of this function? A squared minus 0.1 times b squared. Yeah, there's no minimum, right? It can just keep going to infinity because there's a minus b squared. As the second coordinate increases, you can keep going lower and lower. Okay. And you can still compute the gradient. The gradient is still fairly simple. So we can run gradient descent and see what happens. Yeah, I mean, they are still decreasing the function value, which is good. We expect them to decrease. But they're kind of flatlining here. Ideally, we would like them to go even further down, but they're not doing that. Okay. And the plot of a squared minus b squared, the contour plot has this hyperbolas, right? And you can see they're all going in completely different trajectories. Okay. They're not converging to the same point like before. They're all doing their own thing. They're all meaning here the only difference between these different runs is the step size. Okay, you're starting from different points and changing the step size. And you can see black is going somewhere, maybe green is following that, these two are going somewhere, red is doing something else. Okay. Yeah.
The plot, like, why shouldn't it be one direction? Which direction is the one that's negative? Which axis? Sorry.
I think it's the second one, which is negative.
Why is it symmetric?
Because it's b squared minus b squared.
Oh, okay. Sorry. That makes sense. Thank
And
you.
as a increases, as b becomes bigger and bigger, you're taking
Right.
more and more negative out. Okay. Yeah.
I feel like comparing to starting position. So starting position is step size. Which one matters more?
In this case, I'd say actually starting position matters, and you can actually see it here. If you draw the plot, like it has a saddle in between, like a saddle, like a horseback saddle, and where you are can really change. Like if you're at the top of the saddle, you might never move, might not make any progress, right? And you can see everything is doing its own thing, right? But this is meant to illustrate the gradient descent looks amazing and cool, but even for simple functions like a squared minus b squared, you will have completely different trajectories, completely different things happening. Okay, yeah.
Like, shouldn't the saddle be like parabolic downward? If it's like,
I might have rotated it to make it.
but the coefficient in the long run shouldn't matter. I mean,
Right, in the long run. Right.
I'm not really talking about this plot as much as like the plot of because anything following along the bottom ridge of the saddle should eventually be quadratically declining.
Right. Are you asking like, why aren't we getting there, or?
I'm just saying like the plots that don't look like they're quadratically declining for the gradient descent plots.
Here.
Or up one more.
Right. I mean, they're not declining. That's basically what I'm saying. Like, they're not improving as much as we would expect them to. Like, they're flatlining somewhere here, right?
Because of the step size.
Because of the step size, or just imagine, that you ended up at 0, 0. What's the gradient at 0, 0? It's a squared minus 0.1 b squared. The gradient is going to be 0, 0.
They're not at 0, 0.
They're close to 0,
Okay,
0.
all right.
Right? They're getting somehow converging to close to 0, 0. But like, once you're at the top of the saddle, gradient descent is not going to make much progress. Okay. So once you push it one way, then it'll start going again.
If you did plot this for longer, eventually it should be quadratic decline, right?
Yeah, hopefully. But the rate is pretty low.
I'm just looking at that bottom, and the bottom graph, there's that blue one that is
It is
finding the edge of the
exactly. It seems like it's going in there. Maybe if you run it for enough steps, then you'll start seeing the decrease. Okay. You can see the red one is like, seems like it's getting stuck. So even for the simple functions, we have to be a little careful in how we choose the step size and in trying to reason, like, okay, what are we getting out of gradient descent? Okay. All right. So let me now go back to our thing. Okay. So what did we learn from those things? Step size can matter, right? And even small modifications to the function can change what happens to different trajectories. Okay, like, a squared plus b squared, most things are kind of moving at least towards one another. A squared minus b squared, it seems like they're going in different ways. Okay. And what we're going to do next is kind of reason a little bit about what step sizes are okay. And then more generally, when can we say that GD does something that we want? Okay. And we will then use those insights to change the algorithm for the better. So recall, goal, you have some function L that you're trying to minimize. And GD says for I equals 1 to t, okay. And I want to do one change of notation. When we talked about ERM, we said the examples are x comma y and the parameters are theta, right? But once we start analyzing gradient descent, it becomes cumbersome to keep writing theta, theta, theta. Instead of that, x is an easier thing to have in the calculations. Okay, so let's think we just have So our goal is now we have some function f in d dimensions, and our goal is to minimize this function. Where this function comes from is not important to us for the time being, at least. Right? And then the iteration is just this. Okay. You are going to apply this to ERM, but also you can apply to many other functions, right? So let's study it in generality, and then we'll specialize to ERM later on. Right? And last class, we ended by saying functions like this are probably better than things which are too spiky. Okay. So we want to quantify spikiness of functions. And the one definition that's kind of used universally is Lipschitzness. Okay. It's basically a fancy word for saying that your function doesn't change too much when I change its input a little bit. So you want to quantify how much the function value changes when I change my input by something. Okay. So we'll say f is L Lipschitz. And recall again, it's a d-dimensional function. If I take 2 points, x and y, the difference in their function values is proportional to how much x and y, how far x and y are. Okay. So for all x comma y is less than or equal to L times the distance between x and y. Okay. And you measure distance is Euclidean distance. Okay. So if I only change, my point by moving 1 unit away, then my function value only changes by L. All right. So this is the first kind of level of smoothness of the function. The other thing that we need is continuity of the gradient itself. So what do I mean? Let's take an example. Maybe my function is just a single variable function, and f of x is 10 times x. Is this a Lipschitz function? Yes. Now, when I change x by something, in fact, we have an exact equality. So this is just 10 times x minus 1. Right? So f is 10 Lipschitz. Okay. And in the same place, if I take the function, which is, let's say f of x is absolute value of x. Here, the plot is going to be right. This is what absolute value looks like. Okay. And this is also 1 Lipschitz. Okay, when I change a little bit, my function value is only going to change a little bit. All right. But between the two, which is a nicer function to optimize? If I take 10 times x, it looks something like this, right? Absolute value looks like this. Between these two, which function do you think is nicer to optimize? Any guesses? Yeah. Okay, so that's a good point. But let's say I make it 1x. Then which one would be nicer? So I want to say that this is nicer because not only is the function not changing much, but the gradient is also not changing, right? Here, when you're near 0, right? When it changed from like something like minus 0.1 to plus 0.1, the function value didn't change much. In fact, it's the same function value. But what happened to the gradient? It went from 1 to minus 1. Okay. The small change in the input caused a big change in the gradient of the function. And this could also be bad for gradient descent, right? Because if you look at the gradient descent algorithm, what you're working with is really the gradient. Okay. If a small change in your input can cause a big change in the gradient, then your trajectories will be very sensitive. Even if I start from the same point, if a small change in the gradient, you might go in completely different ways. Okay. So this motivates the next definition, which is smoothness. Not only do we want the function to not change much, but a nicer property that would be useful is to say the gradient also doesn't change much. Okay. So this is smoothness. Now we say f is beta smooth if for all x comma y, essentially the gradients are Lipschitz. Okay, so all distances are Euclidean distances. Okay, so just to recall, if I have a vector in d dimensions, then its Euclidean norm is okay. Any questions? Yeah.
Going back to the Lipschitz example,
Mhm.
on the straight line y equals x, is it Lipschitz or 10 Lipschitz?
Y equals x is 1 Lipschitz. Y equals 10x is 10 Lipschitz.
That's
right. Yeah. I changed it to 1 Lipschitz in between. Okay. And these two conditions are somewhat incomparable. Sometimes you might have smoothness without Lipschitzness. Sometimes you might have Lipschitzness without smoothness. Okay. So as an example, f of x equals absolute value of x, we said is 1 Lipschitz. Okay, small changes in the input don't change the function value much. Okay, but it is not smooth. Right? Why is that? You know, the gradient at a point which is minus, let's say 0.01 is -1. The gradient at 0.001 is 1. Okay. And more generally, if I take any small value here, if it's negative, the gradient is -1. If it's positive, the gradient is 1. Okay, so it's not smooth for any finite beta. Okay. And on the other hand, we can take a different example. Let's say f of x, again, it's a univariate function. Right? Now, what is its gradient or derivative? It's 2ax plus b. Is f Lipschitz for some bounded Lipschitz constant L? No, right? Because when I change x and y, how much the function value changes depends on where you are. Okay. So, you know, f of x minus f of y is ax squared plus bx minus ay squared minus by, which is okay. So this is not going to be proportional just in terms of the gap between x and y, right? When I change the function value from like let's say x is 1 and y is 2, the gap is something. When x is 1000 and y is 1000 plus 1, it's going to be much bigger gap. And Lipschitz says that cannot happen. Okay. So f is not Lipschitz for any finite. Okay. And in general, even if you put a bound on the range of the values that you take, it just means that the Lipschitz constant is not as good. Yeah, but it's not that f is really terrible for optimization, but it's still a nice quadratic function, which we expect is nice to optimize. So what's the advantage? Well, if you look at f prime of x, what did we say it was? It is 2ax plus b. Okay. And if I take another point y, then the gradient is 2ay plus b. So what is the difference in the gradients? Okay. So while f is not Lipschitz, it is 2a smooth. All right. So we saw an example of a function which is Lipschitz but not smooth. We saw an example of a function which is smooth but not Lipschitz. Right. Typically, you'll assume both, but smoothness is in some sense nicer to analyze. Lipschitzness turns out to be more ubiquitous. Okay, any questions about this? Yeah, sure. Okay. Any questions? Okay. So now, so why are these assumptions useful? You'll see that you can use these parameters to choose the step size. Okay, this is why theory is important in the sense, at least for this case, is that one immediate application is if I know some kind of bounds on how smooth the function is, then it can tell me how big a step I can take. If the function is very smooth, I can take big steps. Okay? Whereas the smoothness beta is very, very high, I have to take tiny, tiny steps. Okay. And sorry?
What are the Lipschitz?
Sorry?
What are the Lipschitz?
Yeah, Lipschitz property again can be used for similar things, right? Lipschitz property can also tell you how big a step size to choose, but that's a little bit harder to analyze. Okay, so we'll work with smoothness first, and later on I'll tell you, just without proof, the analogous statements for Lipschitzness. Okay, you get weaker guarantees with only Lipschitzness. It's a good question. Okay, so all right, so let me do something. Here's our first sort of formal claim about gradient descent. Have some function. Okay, I want to use gradient descent on it with some steps in this. The least, the minimal thing we can expect out of gradient descent is that the steps do not hurt you, right? Meaning I'm trying to minimize the function. I go from xi to xi plus 1, my function value decreased. Okay, that's kind of a minimal expectation that we can have. You're making some progress, even if it's not much, you're not kind of retracing your progress, right? So and is, let's say, beta smooth. Okay. If your step size is smaller than 1 over beta, and if you're 100 smooth, then you'd want to say your step size is at most 0.01. If you're 10 smooth, your step size is at most 0.1. Then gradient descent is at least monotone. Okay, so let me say this is the monotonicity of gradient descent. Okay. So as long as my step size is not too big as quantified by the smoothness of your function, I am making some progress. Now, how much progress do I make? The amount of progress I make depends on how big is the gradient at my current interval. Again, it makes intuitive sense, right? And if your function gradient is 0, your update does nothing. Xi plus 1 is xi minus eta times the gradient. Okay, so if this is 0 or very small, you're not doing anything. Okay, and this is actually making it quantitative. If my gradient is big and my step size is something, then I'm making progress. All right. Any questions about this statement? The nice thing here is that it's very generic. You're not assuming something, some nice properties of the function, only smoothness. Yeah, as far as assumptions go, smoothness and Lipschitz are one of the easiest to get. All right. Okay. So let's take a 5-minute break, and when we come back, we'll prove the statement. The proof is, again, we'll follow from some properties of, what does gradient give you? Why is it a good step to take? All right. Okay, we'll start in 5 minutes. Okay, so the proof relies on, let me say something. Let me draw a picture the best I can. Yeah, I'll try and make it colorful. Okay, so let's say this is our function. We are going to assume it's smooth. From the picture, what can smoothness tell us? Well, okay, first, what's the geometric interpretation of the gradient? Right, so gradient is basically slope of the tangential line at any point. Right, so if I go here, I can draw a tangent line. And the slope of this line would be the gradient at this point. Okay, and the same thing here. Even here, the tangential line would be something like this. And then the slope of that line would tell me the gradient. Now, how about smoothness? What kind of, what does smoothness tell me about the curve pictorially? It actually tells me something very nice, and this is an important property of smoothness which gets used all over the place, and I'll call this smoothness upper bound. So smoothness intuitively tells you that the gradient does not change too much when you take small steps. And if you tug on this thread, you can actually conclude that your function itself doesn't change, much faster than a quadratic function. Okay. So in particular, so let's do it for the univariate case. I have a univariate function, so I'm just dealing with derivatives. Then if I consider a point, like let's say A here, okay, and then try to look at the function value at something like A plus H. Okay, maybe let me choose this point. This is A. If I look at its function value at A plus H. Smoothness tells you, if you use some calculus, you can conclude that f of A plus H is not much more than f of A. How much more can it be? The best you can do is as if the function was a parabola centered at A. So the orange line is basically supposed to be the parabola which is centered at A comma f of A, and its equation is beta over 2 times h squared. Okay, so this is parabola which is roughly beta over 2 times h squared. Okay, so if we take such a parabola, then that is always going to dominate the function, and this is true not just at A, but basically at every point I can define a corresponding parabola. Okay, my drawing skills are limited, so kind of bend your mind with me and think these are all parabolas which are nicely touching. All right. So for every one of these points, I can define a parabola. And what's good is that every one of these parabolas is always going to be above the purple curve, no matter where you are. Yeah. So it's only giving you an inequality in one direction. It's just saying that you're not going to cross this parabola. Okay. And maybe it should be definitely be like this. Let me draw one flatter one. Right. So if I keep extending it, you're going to look something like this. Okay. Yeah. We don't need Lipschitzness if you have smoothness. As I said, smoothness is by its own is a good enough condition. But even though technically smoothness doesn't imply Lipschitzness, in practice, Lipschitzness is easier to get. Like, we saw an example of a function which was Lipschitz but not smooth, right? But those functions are rare. Most often, smoothness is a harder constraint to have. Okay. And one thing to keep in mind is that even though you have this parabola, there's a different parabola. If it was all dominated by one nice parabola, that's good. But some parabolas are kind of centered here, some are here, so they're different. For every point, there is a parabola that I can draw, and your entire purple curve is going to be below that. Okay, yeah.
As like some upper bound on the absolute value of the second.
Yeah, for sure. It's basically the spectral number. I mean, in the one-dimensional case, is the max value of the second derivative. Yeah. Absolutely. That's a kind of, that's an analytic way to define it. And that's one way you can actually calculate it if you had to. Okay. Any other questions? Right. So the proof of this, it comes from calculus. I'm not going to prove it. But let me just say, so, why use Taylor's theorem? Okay, calculus 101, Taylor's theorem tells you this kind of every function, you can expand it out based on the first derivative. What's the first derivative, and then how the first derivative changes. And because of smoothness, you can bound this difference, and that gives you the upper bound. Like, basically this is less than or equal to beta times t times h, and then you can do it. Okay. All right, so let me not belabor that. And okay. But let's just take this for granted. The important thing is that smoothness gives you this kind of growth upper bound. Your function is not going to grow too fast. How fast can it grow? It can grow as best as a parabola centered at that point. Okay. So now that we have the smoothness upper bound, let's see what it tells us about gradient descent, right? So let's look at our equation. So what is gradient descent? You go from your current iterate xi to some step size times the gradient. Okay. Let's start recording. Okay. So what is the new function value? Right. So we want to say that the new function value is smaller than the old function value, and also want to quantify how small it is, right? I mean, this bound is kind of tailor-made for that. It's actually telling you, if you take some step, what's the new function value going to be at most, right? So I can just use that upper bound. Okay, so this is f of xi minus eta times f prime of x. Okay, we are in the univariate case first. And this is like our h, right? I can use my smoothness upper bound to say this is at most f of xi plus h times f prime of xi plus beta over 2 times h squared. Okay. Now you just plug these values in. H is negative times the gradient. And so you simplify it, you get something very nice, which is, you can see that you have the square of the gradient in both places. The coefficient is changing. You have minus eta and plus Okay, so the square of the derivative is a positive number. We want the function value to decrease, so we want this thing to be positive as well. Okay, so in particular, if beta is less than or equal to 1 over eta, then okay, so all we did is basically plug in, substitute the equation for the gradient update into this. Okay, any questions? Okay, so at least in the one-dimensional case, it seems that you have monotonicity. How about the higher dimensional case?
Like a proof of
Yeah. So proof of lemma, but only for d equals 1 so far.
dimension 1.
Dimension 1, and now we'll see how to extend it to. So this proves lemma when d equals 1. Okay, and in general case, nothing really needs to change. We just need to make some adjustments to the claims. Okay. Well, maybe no, I can't do this. Let's take the smoothness upper bound and state it more generally for higher dimensional functions. Okay, now your function is seems that this app has crashed now. So if my function is in higher dimensions, what happens? Okay, so what do things, how do things need to change? First, you might have you have a gradient now, not just a derivative. Okay, and the smoothness upper bound now looks something like this. Okay, so products become inner products and squares become square of the norm of the vector. Okay, and recall for two vectors u comma v, the inner product is the sum of the products of the individual products. Okay, it's all geometric in the sense that all you're looking at is how much is my step h kind of correlated with the gradient step, and you're quantifying it by how big your gradient step is in terms of the norm. Okay, and the rest is similar. So now you have the update xi plus 1 is xi minus eta times gradient. Okay, so let's plug that in. This is going to be our h, so less than or equal to f of xi plus gradient f of xi, inner product with negative gradient. Okay. Now, if I have a vector u, what is the inner product of u with itself? Yeah, it's norm squared, right? So this is one reason why Euclidean norm is particularly nice for gradient descent, because when you take the inner product of the vector with itself, you just get the norm squared. Okay. So just plug that in, you get f of xi minus right? And as from our assumption, your step size was smaller than 1 over beta. So this is less than or equal to
Usually assume that all of the step sizes for each of the
that's a good question. Like, they don't have to be, right? That's what we're using, to begin with. And typically, let me say a few words about that in a second, but you can try and use different step sizes, right? And the only thing that we are really using in this analysis is that in the current step, the step size is at most like beta or 2 or 1, sorry, at most 1 over beta. Okay. So you can change the step sizes and do more things as well. Okay. But at the very least, we got the, like this is QED, right? So we get monotonicity of GD for smooth functions. So your function could be crazy. It could be like a squared minus b squared. It can have all kinds of things. As long as it's smooth, you're not going to hurt yourself too much by doing gradient descent because step size isn't too big. Okay. So along the lines of the question that was just asked, let me, say some things about what people do for some applications in practice, right? So what did we just learn? We learned that GD makes progress as long as, okay, and some practical tricks that kind of come out of this step is, we suppose you don't know what the smoothness is, and maybe your function is in some places much smoother than in other places, right? You could tailor the step size that you're taking to the smoothness at that particular point. Okay? Like, maybe you're in a very sort of spiky region, or maybe you're in a reasonably smooth region. You can adapt your step size accordingly. And one way to do that is kind of do this sort of greedy search, where you say find largest eta such that we know there is some such step size. As long as the step size is sufficiently small compared to the smoothness, you're not going to hurt yourself, right? Maybe I'll take the biggest possible step as long as I don't hurt myself. Okay. This is something you can do. So for instance, you can start with the big eta, like, start with eta equals 100. If this is violated, maybe try eta equals 50. If that works, then, you're fine. Otherwise, kind of, try other values. Okay. And people also sometimes do what's called backtracking line search. To figure out the best eta to use. Now, how big a step you take doesn't have to be the same across all iterations. It can be tailored to where you are on your function landscape. And one way to do that is to kind of quantify the smoothness at that point. Okay. Yeah.
You also tried to estimate the second derivative.
Right. I mean, you can definitely do that, but in practice, second derivative is very hard thing to compute. Basically, the second derivative, like if you're in d dimensions, right? Second derivative has d squared values, right? So it's quadratically over, and it's like really expensive in practice. If you can compute the second derivative, then there are even more efficient, different algorithms you can try. Okay, I'll say a few words about that later on. The good thing about this is that all of this kind of, trying to find the best eta using backtracking, line search, and so on, you still only need the first derivative. Here's that's advantage. You're only working with d-dimensional things instead of d-squared dimensional things. Yeah.
Just going back to the physical analogy. Makes sense to have like some memories.
Yeah, we'll get to that. I mean, that's a very important idea, which has tremendous impact in practice. And as I said, this is a vanilla gradient descent. We'll see its limitations and then talk about what else can we do. Okay, first we need to abstract, okay, what do you mean, what else can we do? Of course, if I have a full function, I can bring a full set of tools to it, right? But we'll see, given some limited access to the function, what's the best algorithm we can use. And there, this intuition from physics has been very, very influential, both in theory and in practice for most of the modern machine learning systems. Okay, yeah.
The backtracking line search, what exactly are you backtracking?
Like essentially, like you choose a big eta, you think this is violated, then you backtrack your eta. It's like
Okay.
that's yeah.
Is that so? What's the difference between?
So here you might basically use like binary search or something, right? This is a way to do this essentially.
Checking is you just hit again and see how.
No, you just change the eta. You're only changing the step size.
Go back to the point, change the eta.
And then exactly, yeah. So that's like you're not moving from xi until you decide on which eta to use, and then you just keep going with that eta.
Is it significant that we're bounding it by the square norm of the gradient as opposed to because the step?
So this is the right scaling. Like smoothness is really telling you that maybe you can assume your function is quadratic. And for quadratic things, basically the second derivative, the derivative squared is what's going to show up. Okay. You want to make sure that everything is consistent in kind of scaling and dimension and so on. All right, any more questions? Okay, so at least with smoothness, we know how to set the step size and some rudimentary. I'm saying rudimentary because it's just saying your function isn't improving, isn't hurting. You're not hurting yourself, and you make some progress as long as your gradient is not too small. But it doesn't tell you that the gradient is not going to be too small, right? So, like for instance, if your function is like this, you start here, you come here. The monotonicity property becomes useless once you get here. Right? You start here, it tells you, okay, you decrease your function value, but amount you decrease is becoming smaller and smaller. Right? This is colloquially known as the problem of vanishing gradients. In sense, you think there's further progress to be made, but your gradients have vanished, they become zero. So gradient descent is in some sense getting stuck because the gradients are so small. Okay, and the reason is because you're here as opposed to coming in here. Okay. So are there interesting cases where such a scenario doesn't happen? Okay. Are there some nice cases where this doesn't happen? If this doesn't happen, what can we say? How many steps do you need? Or are there faster things we can do? Okay. So to that end, I want to introduce one of the most important objects in optimization and theoretical computer science, which is the class of convex functions. Okay. So this is a really magical ingredient in optimization. Has many applications. In theory. Okay. So in theory, it has a huge number of applications in theoretical computer science. You can use that to solve all kinds of like combinatorial optimization problems and so on. But also in practice, most functions that we deal with in machine learning systems, if you use a deep neural network, it's far from being convex, right? But then why study convex functions? Because they give us insights into what algorithms to use more globally. Okay, so you're going to look at convex functions as a test bed for how well gradient descent can do, and use insights from here, kind of speed up gradient descent here, and then carry them to general functions. And this is not just like a experiment that we are going to do. This is how history has played out. People kind of develop this faster algorithms for convex functions first, and then use these for more general functions. Okay. So I would say it has very good applications in theory, and also gives you very useful practical insights. All right. Okay. So what's a convex function? I mean, essentially, convex function is something that looks like a parabola, right? It's like a bowl, meaning it doesn't have this double dips, which is, as we have always been saying, that seems to be the main problem with gradient descent. If you have a double dip like here, then you might get stuck here instead of going here. A function will be convex if it doesn't have such double dips. Okay. So there are various definitions of convexity. You can define it analytically in terms of the second derivatives and so on, but I'll state it two ways: one geometrically, and then kind of by an equation. The geometric way is to say you have your function. At any point, I can draw the tangent line, or if you're in 3 dimensions, the tangent plane. Okay. The tangent line for a convex function is going to be always below the entire curve. It's never going to intersect the curve again. Okay. So like here, if you think of the tangent line, it's actually crossing the function again. Right? If I think of this tangent line, it's above the function curve. So that means that this function is not convex. Okay, so pictorially is convex if the tangent plane at any point is below the curve. Okay, so for example, this is not exactly not a parabola, but still it's convex because you can see that the tangent line at every point is completely below the curve. Right? Take any point, draw the tangent line. It's below the curve. And in 3 dimensions, also something similar happens. You just want it to be imagine you have like this distorted bowl kind of surface which is going up, and you'll say, for any point, if I draw the tangent plane now, Okay, so this entire plane is below the surface of the curve. Okay. And formally, you can define it by saying, if I take 2 points, maybe let me draw a different picture. So I have my curve here, right? If I take 2 points, let's say X and Y. Right, so this is the point X comma f of X and Y comma f of Y. The line segment joining these 2 points is above the curve in between. Okay. So in particular, if I take the midpoint of X and Y, then the function value at the midpoint is less than the average of the points. Okay. So for all X comma Y, the value of the function on the average of 2 points is at most the average of the 2 values. Okay, this has to be true for any 2 points. Evaluating the function on the average is only going to be at most the average of the 2 evaluations. Okay, first evaluating and taking the average is going to give you a higher number. All right. So that's one definition, and there's equivalently many definitions, as I said. Equivalently. Is convex. I mean, some of these things, the equivalence of these 3 properties are a little, they require a little bit of proof, but again, I'm not going to do that here. We're going to look at their implications rather than why they're true. Okay, so this is one definition, as I said, and this is equivalent to saying not just the average, but if I take, let's say, some other, like maybe 1/3 of X and 2/3 of Y, even then a similar property holds. So for all X comma Y and lambda, which is between 0 and 1, evaluating at a point which is lambda fraction of X and 1 minus lambda fraction of Y is at most okay. And finally, the property that is most useful for us actually is the following. So what's the equation of the tangent line here? Well, it's a line. Think of 2 dimensions. So here's my X comma f of X, right? So what's the slope of this line? It's the derivative, right? It's f prime of X, its slope, and it passes through the point X comma f of X, right? So I can write down the equation. I know the slope of the line. I tell you, a point it passes through. I can write down the equation of the corresponding line, right? And what is the equation going to be? So the equation is going to be y equals okay, so the tangent line is given by, sorry. Okay, at any point y, the tangent point is given by f of X plus f prime of X and y minus X. I'm just kind of interpolating. I know the slope. I know the point x comma f of x. So if I substitute y equals x, it passes to the desired point. Okay. And as I said, one definition of convexity is that the tangent curve should be below the line completely. Okay. So meaning for every x comma y, right? So if I take any other point y here and look at what this tangent line tells you, that value should be less than f of y. Okay. So this is the equation of tangent. Right. So convexity gives you a nice lower bound on your function. Smoothness gave us like this upper bound kind of parabola thing. Convexity gives you a lower bound. Right. So for every point, I can draw the tangent plane, and your function is never going to be much smaller than whatever this tangent plane tells you. Right. Any questions about this? Okay, it seems, okay, so the convexity has these properties. Are there many convex functions? Why are convex functions good? One of the reasons there are so many convex functions is that you can compose convex functions to get convex functions as long as you do the composition in some nice way. Okay, so give you convex functions, you can put them together to get new convex functions. All right, so let me say some properties and give some examples next. One, f comma g are convex implies f plus g is convex. Okay, if I add up two convex functions, I still get a convex function. And the proof of this, you basically look at this inequality. If it's true for f and g, it will also be true for f plus g. Okay. What about scaling a function? The scale, what happens? As long as the scaling is positive, you'll have convexity, right? If you have parabola, if I scale it, maybe it will become a steeper parabola or a flatter parabola, but you're not changing the shape. Okay, and finally, if I have a univariate function, single variable function, and I have a vector in d dimensions, I can define a new function in d dimensions, which basically takes the linear function corresponding to w and applies g afterward. Right, so you're basically thinking of g as like the activation function. So you take the inner product first and then apply g. Okay, so if your activation function g is convex, then the new function in higher dimensions is also convex. Okay, so this is one way to build higher dimensional convex functions starting from something in one dimension. Yeah.
Your function.
Yeah, it is considered convex because it will satisfy these inequalities.
Then a like or multiple
A just has to be non-negative. That's a good point. Okay, and there are other functions which are kind of important functions which are convex. So e to the x is a convex function. Okay. I mean, if you draw e to the x, what does it look like, right? It's 0, it is 1. Okay, so this is e to the x, right? You can check minus ln x is a convex function. I mean, basically log is concave, so the negative is going to be convex. And x squared is a convex function. Okay. So convexity becomes more and more powerful as a property when you're in higher and higher dimensions, right? So for instance, you can also show that the Euclidean norm squared function is convex, over R. Over real numbers in higher dimensions. The absolute value function is convex. Okay, again, all of these things you can check by just drawing the figure and so on. All right. And in the next class, we'll see that once you have convexity, gradient descent not only does it not increase the value, but will actually converge to the true minimum. And we can quantify how fast it converges. All right. So we'll start with that in the next lecture on Monday.